Welcome back to our specialized series on industrial artificial intelligence. Today, we are exploring a fascinating concept called logistic regression. Imagine a student named Alex. Alex has a big exam coming up and asks, "If I study for 5 hours, will I pass or fail?" That's a binary decision, only two options: pass or fail, yes or no. Now suppose the school has passed data from hundreds of students. How many hours they studied, and whether they passed, which we mark as 1, or failed, which we mark as 0. The question is, can we use this data to teach a model to predict whether a new student with a certain number of study hours is likely to pass? That's exactly the kind of problem logistic regression was designed to solve. Before we dive into logistic regression, let's briefly remember linear regression. Linear regression draws a straight line that best fits the data and predicts a continuous value, like an exam score. For example, with exam scores, the input is hours studied, and the output is the predicted score in marks. We calculate linear function with hours studied plus bias. Then we calculate mean square error to determine if hours studied and marks are correlated. Then calculate p-value to find if the mean square error is statistically significant. You give it 5 hours studied, and it might return a number like 73 marks. That's great when we want to predict a continuous number, like the exact score. But Alex's real question is not, what exact score will I get? It is, will I pass or not? Passing or failing is a yes or no classification problem, not a continuous prediction. You might still think, can't we just use a straight line and then say, above some value equals pass, below it equals fail? The problem is that its predictions are not restricted between 0 and 1, so it can give values like -0.1 or 1.3. It is not good for squashing. It keeps stretching upward or downward in a straight line. That does not make sense if we want to interpret the output as a probability. So for classification, we need a method that can squash values between 0 and 1. That is exactly why logistic regression is used instead. That is where the sigmoid function comes in. The sigmoid function takes any number and squeezes it into a value between 0 and 1. Tries to find a curve in S-shaped probability curve that rises from mostly fail to mostly pass as hours studied increase. Logistic regression works like this. First, it builds a linear formula like a straight line model using the inputs. Then it passes the result of that formula into the sigmoid to get a probability. If we look at this in the input space, we can also draw a decision boundary. If the output is close to greater than or equal to 0.5, it means the answer is probably yes. If it is less than 0.5, it means the answer is probably no. You can think of sigmoid as a probability machine. It turns a raw score into a maximum likelihood. Let's go back to Alex in the exam. First, the model takes that input. Then it calculates a score using the learned pattern from the training data. Next, it passes that score through the sigmoid function to convert it into a probability. Let's say the result is 0.8. That means there is an 80% chance the student will pass. If the probability is equal or above 0.5, the model predicts yes. If it is below 0.5, it predicts no. We'll probably see that students who studied more hours tend to pass more often, and those who studied very little tend to fail more often. So logistic regression is learning where to place that boundary so that it separates passes from fails as well as possible. Now let's discuss practical example, loan approval. A bank wants to decide, should we approve this person's loan, yes or no? They have passed data, income, credit score, existing debt, and whether the loan was approved, marked as 1, or rejected, marked as 0. We train a logistic regression model on this data. Now a new customer walks in. The model takes the person's information and does the following. First, the linear step. It multiplies each feature, such as income and credit score, by a learned weight and adds them up to get a raw score, which we'll call z. Second, the sigmoid step. It feeds z into the sigmoid function to get a probability, say 0.78. Third, the decision step. If 0.78 is above the threshold 0.5, the model predicts approve. If it were 0.2, it would predict reject. Notice that the bank can either use the probability directly, like 78% chance of repayment, or use the yes or no decision based on a cutoff. So why do people love logistic regression? It's simple and fast to train. It outputs probabilities, not just labels, which is very useful for decision making. It's interpretable. You can look at the weights and see which features push the prediction toward yes or no. That's why logistic regression is used in medicine, finance, marketing, and many other areas. But it's not perfect. Logistic regression struggles with very complex, nonlinear patterns where a single boundary is not enough. It can be sensitive to outliers. Extreme data points can pull the model in the wrong direction if you're not careful. When things get more complex, we might need decision trees, random forests, or neural networks. But logistic regression is an excellent first model and a great way to understand classification. So to sum up, logistic regression is used for binary classification, yes or no, 1 or 0. It uses a linear model plus the sigmoid function to produce probabilities between 0 and 1. It learns a decision boundary that separates the two classes and uses a threshold, often 0.5, to turn probabilities into final predictions. With this intuition, you can now look at many real-world problems, exams, loans, spam, customer churn, medical diagnosis, and say, hey, that's a logistic regression problem. The future of industry is intelligent. Let's build it together. Thank you for watching.